Hi, my name is Madelyn and I'm presenting on behalf of the MIT, Boston University, and Waterloo team for our project called the Space-Based Solar Power for Operational Robustness in Lunar EVAs and Exploration Architectures. I do want to emphasize that my co-authors, Anna Tretiakova and Vanessa Chen, were the two who actually presented this poster at IAC. Just due to the distributed nature of our team, we weren't able to get together to do this recording, but they should receive full credit for that presentation. So to dive into our project, the driving need for space-based solar power in large architectures is because there's currently a single point of failure in the mission plans for these long-term lunar missions. There's a reliance on surface nuclear power as the only power supply. This is something that could seriously impact astronaut safety in a crewed mission if, for example, we have a power system failure or an unexpected surge in power demand. The likelihood of having either of these occur increases as we have larger and longer missions. Additionally, crew exploration is limited in a fixed power supply model. This type of architecture is inflexible to changing EVA requirements, such as those that might request us to explore away from a base location. So space-based solar power is therefore needed for lunar exploration architectures that promote long continuous habitation, a wide range of exploration locations, again, away from that base location, and access to higher risk locations because we want to mitigate the risk as possible in areas that we can by providing this redundancy. To dive into Martimus here, we're using Martimus as a case study because it's this large distributed architecture with long-term habitation. So it kind of is a good case study for the scenarios that we're proposing here. Martimus targets an energy-rich architecture with system redundancy, autonomous operation, and long service intervals. Space-based solar power provides a critical component of this within the energy architecture. Again, it provides critical system redundancy complementary to that surface power generation infrastructure. It also enhances the ability to meet the surface exploration objectives that are designated in the mission, as we'll explain as we go forward. So the solar power architecture therefore must provide full surface lunar coverage with the ability to provide backup power to the habitats in case of that power system failure, but also to charge rovers quickly to promote that exploration architecture. When we get into the constellation design, we've done a full trade study of a lot of different potential architectures here. The minimum number of the satellites needed for full coverage per orbital plane was calculated assuming a circular orbit, and the details of this calculation are included in the paper. But if we isolate the range of these possible orbits, we can kind of downscope to just looking at the stable lunar orbits that won't be thrown off by mass cons and things of that nature. So what we end up finding in doing this full trade study of the different possible combinations of orbits and architectures for our satellite system, we get that the constellation using a minimum satellite of 6 or less results in an upper limit for the altitude that's lower than the lower limit for the altitude. As such, the lowest allowed minimum number of satellites in our constellation is 7. And again, this is being driven by that need for full surface coverage. So we want to find the minimum number of satellites that we can use to get full surface coverage of the moon in these allowed orbits. So again, we settle on a minimum number of satellites per constellation in 7, being 7. We increase that number to 9 to allow for a one-out constellation design. So if something happens to one of those satellites, we can continue this operation. Each satellite in the constellation is equipped with a laser on board for power transmission, a battery system to power the satellite and to store the power that's being transmitted, thermal control, focusing systems, and solar panels, as well as for the case of the Martimus missions, we include communication and navigation systems on board those satellites as well. Again, because we have that full surface coverage constellation, we should get the full utility out of it. The main role of this satellite, of each satellite, is to utilize laser power transmission to charge rovers on the surface of the moon. And so the way this works is that each satellite over a target location supplies the receiver with 0.2 kilowatts of power every 2 minutes. The rover receivers are intended to be turned on when the rover is stationary and off while the rover is moving whenever possible. This is to avoid jumps between charging and not charging states as the rover crosses coverage zones. Once we're parked at an EVA site, though, the receiver can be turned on and the rover is recharged through normal satellite movement over the receiver cone. Operationally, this works really well for EVAs with periodic pauses for sample collections because this avoids incurring wait times for the rover to charge. For longer EVA drives without designated charging breaks, a strategic power cycling method can be applied to extend the lifespan of the rover batteries. For example, if you drive the rover until the battery is discharged to about 20%, then turn on the receiver to charge while you're driving, you can reach full charge and then turn the receiver off until stopping or reaching that 20% charge again. So you can cycle the power and not just leave that battery on the whole time. We expect this to extend the lifetime of the battery on that rover. Artemis, as a mission, provides 332 long EVAs and 124 short EVAs over a 109-month surface mission duration. The calculations of all of this, including those EVA numbers, are detailed pretty heavily in the paper, so please take a look at those. This provides, again, a lot of EVAs, a lot of EVA time that we don't want to constrain to just that base location. This is really important that we enable our astronauts to do the exploration function that they are on the surface of the moon for. When we look at the cost, though, we're adding a new mission component just for, in some views, just for the sake of redundancy. Again, it has other utility, but if we look at it even just from that perspective, we need to consider how affordable this is in the mission architecture. So taking Artemis as this example, the representative architecture that we're considering here gets an estimated life cycle cost of $91 billion. With anticipated cost sharing and international partnerships, the cost to NASA is then estimated to be $25 billion using a cost model that is laid out in the paper. A constellation of 30 satellites adds a system cost of approximately $720 million following this same cost model. This only adds 0.79% to the total mission campaign budget, so less than 1% of the cost is added for this significant increase in safety and ability to meet the mission objectives. So this means that we really see a utility for this in our large mission architectures in particular. So as we look at developing these exploration class missions, this is something that could very feasibly fit into those mission architectures. And then just to kind of zoom in a little bit on some of the images and figures that were presented that I can't quite click on as we go through here. This is the Artemis mission plan. This is a simplified CONOPS there to show how we reach the total of 109 months of surface stay. This is broken up over 13 missions and kind of spread out in time from 2034 through 2039. These are the basic calculations that we used to calculate that long and short EVA, where short EVAs might be something that you can do within the course of a day, including rover drive time to and from the location, while long EVAs are things that would take multiple days or even a couple of weeks to do. Again, we get hundreds of each of these in the Artemis mission plan, really driving that need for ability to explore away from the base. This lays out some of our ground track coverage from our satellite constellations, and we use the Apollo locations and the Artemis locations as representative areas, showing that we can achieve coverage when we are at these designated sites of interest. And then the output of this is that we can achieve our charging objectives, our power delivery objectives using this type of a constellation with kind of the metrics laid out as our final output here. So emergency power supply without SBSP is we only have the fission power on the surface. With SBSP, though, we get an additional 20 kilowatts per hour that we can provide to the base locations in case of emergency. We extend our EVA maximum range from 125 kilometers to 1,000 kilometers. Instead of, we can achieve full surface coverage, but we're limited by the length of time of the EVA as opposed to the power supply in this case. And yes, so again, for the EVA lunar surface coverage, this extends our ability to our science objectives to reach 26 geologic units on the moon as opposed to just the 8 that we could reach around the base location. And critically, this only adds less than 1% of the total life cycle cost to the mission. Feel free to reach out with any questions, and thanks for letting us be a part of this project.